Hello everyone, Mr. Minix. My name, math is my game, and today is in Algebra 2, we're looking at Chapter 5, Section 5. The title is Theorems about polynomials, and I'm splitting this section in two because part of it's really easy and part of it's a little bit more challenging. So Chapter 5, Section 5, we're getting toward the end of Chapter 5 here. But this is theorems about polynomials. And I'm not going to expect you to memorize the theorem verbatim with all the little details, but I do expect you to be able to apply them. Okay? So let's just get right to it. The first theorem is called the possible rational roots theorem. The possible rational roots theorem. The possible rational roots theorem. And it's really handy. It's basically what we're going to be using the next 4 days of class. And it kind of serves as giving us a roadmap of where we're going to go. It says for polynomial p of x, for a polynomial p of x equals ax to the n plus bx to the n minus 1 plus ... plus, what's a good letter to end this with? A good constant letter to end this with? Would anybody be offended if I ended this with k? I'm going to end this with k. All right, plus k. Yeah, right. Yeah, this is n minus 1 there. Yep. So early on in the chapter, we defined a polynomial with, descending order by degree. So for a polynomial, p of x equals ax to the n plus bx to the n minus 1 plus plus k. The possible rational roots, the possible rational roots are of the form plus or minus p over q, where p are all the factors. I know that sounds weird to say, but p are all the factors of k, and q are all the factors of a. Now this seems really vague and really abstract at the moment, I'm sure. Possible rational roots are of the form plus or minus p over q, where p represents all the factors of k and q represents all the factors of a. It's very unusual the way this theorem's written, but it's really not as difficult as the way it's written makes it seem. It's really not so bad. What this theorem is really saying is if you want to know what the possible rational roots of some polynomial are, all you've got to do is just look at it. All you got to do is just look at it. You're looking at the constant, and you're looking at the leading coefficient, and that's it. So this k kind of represents it does represent the constant, and a represents the leading coefficient. So if you see a polynomial and you'd like to say to yourself, I wonder what its possible rational roots are. All you're going to do is look at the constant, find all the factors of the constant, look at the leading coefficient, find all the factors of that, and just kind of write them out in fraction form. We ready to see this thing in action? Okay. So here we go. Example 0. List all the possible rational roots of p of x equals 17 x cubed plus 149,000 x squared minus 2x plus, I need a nice number, a number that's got a decent amount of factors, but not too many. What was it? 125? Yeah, 125 will work nice, actually. Thank you. Cool. So to find our answer, remember our answer is going to be of the form plus or minus p over q, and p represents all the factors of 125. So p is really all of 125's factors. So let's think about 125 and think about what its factors are. Obviously, any number is divisible by 1 and itself, so 1 and 125 are some factors, right? Does 2 go into 125? No. Does 3 go into 125? 1 plus 2 is 3. 3 plus 5 is 8. 8's not divisible by 3, so 3 doesn't work. 2 didn't work, so 4 is not going to work. I think 5 does. How many times? 5 and 25, okay. Since 2 and 3 didn't work, 6 won't work. I'm pretty sure 7's not going to work. Since 2 and 4 didn't work, 8 won't work, 9 won't work, 10 won't. I think that's it. Just 1, 5, 25, and 125. Okay? So that's the P that we talk about in that theorem. Now the Q that we talk about is all the factors. Q is all of the leading coefficients factors, all of 17's factors. Now 17's nice and prime. What are 17's factors? 1 and 17. So our answer's of the form plus or minus P over Q. So our answer then to this is going to be plus or minus 1 divided by 1. Now, to be real clear here, to be as clear as I possibly can, this 1 in the numerator is the same thing as this 1 from the P. And this 1 in the denominator is the same thing as this 1 from the Q. Everybody with me so far, I hope? Okay. If I keep on trucking, I'm going to have plus or minus 5 over 1, plus or minus 25 over 1, and plus or minus 125 over 1. Now, again, to be clear as mud, actually crystal clear, all these things in the numerator here are all of P's factors, and all the things in the denominator there are still the 1 from Q being divisible by 1. Everybody with me? Okay. Now, what happens if you divide something by 1? Isn't it the same thing as just having that integer? So it's kind of senseless to put that over 1, right? So I guess if I wanted to, I could probably just say, okay, so plus or minus 1, plus or minus 5, plus or minus 25, and plus or minus 125. But I'm not done. There's still more. They're of the form plus or minus P over Q. Now, Q is all the factors of 17. So we got this one kind of taken care of, but our list is going to be doubly as long, right? Our list is going to be twice as long, because we're also going to have it added to this list, plus or minus 1 divided by what? 17. Good. And then what's next in the list? Plus or minus 5 over 17, plus or minus 25 over 17, and plus or minus 125 over 17. So to be clear, these denominators, this 17, 17, 17, and 17, that's Q's other factor. Okay. So if I were to put that list out in a horizontal fashion, maybe I can do that. Let's see if the smart board cooperates. So plus or minus 1, plus or minus 5, plus or minus 25, plus or minus 125. Get all these other ones and put them beside it if I can. And all those, it looks like there's how many? It looks like there's 8, but remember we got plus or minus. So how many are there really? 16. So there's 16 possible rational roots of the polynomial. Does anybody have any questions so far? Now, one thing I have to point, question. What if it repeats? That's a terrific question. If one of the zeros repeats? Well, the deal with this theorem, look at the name of it, the P word, the possible rational roots. What it's saying is if that polynomial has any roots and they're rational, it's going to be something from that list. It could repeat. And the fact that you're asking whether or not it repeats, that's awesome. I'm glad you asked. And it might seem like way too much work to list them all. And sometimes we don't even have to list them all. But the point is, if the polynomial has any rational roots, they're going to be one of those 16. Some polynomials don't have any rational roots at all. Some of them will have the same root 3 times in a row. You know, it will repeat. So the whole purpose behind this theorem, if I haven't said this yet, the whole purpose behind this theorem is so that, remember last week when we synthetically divided? So that we know what we could synthetically divide by. So here's the heart and soul of chapter 5, polynomials. Here's the big idea in chapter 5 with polynomials. Example 1. Example 1. Find all, getting ahead of myself. Find all the roots of this polynomial. P of x equals 2x cubed plus x squared minus 7x minus 6. Find all the roots of it. So one thing that's kind of interesting about this is it's cubic. The function, the polynomial is cubic. So let's think to ourselves and ask ourselves, how many roots are we expecting this to have? 3. So we know this is going to have 3 roots. Now, the possible rational roots theorem says if there are any rational roots, they're going to be from that list that we make. So let's go ahead and make that list. Our possible rational roots. We're going to have plus or minus what? So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus, not 4, 6. So where these are coming from is 6's factors. These are coming from 6's factors. But our list is going to have a couple more things, isn't it? Because we got to divide by the factors of 2. So what else? So plus or minus, if we divide 1 by 2, that's going to be a new member in our list, right? If we divide 2 by 2, that's 1, which we already got. If we divide 3 by 2, that's going to be another new member of our list, right? And then 6 divided by 2 is already in the list. So those are all the things that it could be. Doesn't necessarily mean it's going to have any. Now, I happen to pick a nice example. This actually does have 3 roots, and they're all rational. This actually has 3 roots, and they're all rational. So here's the deal. Once we do this, I'm going to say throw a dart. Anybody ever throw a dart? What happens when you throw a dart? It hits the dartboard somewhere, right? Pick a starting point. Where do you want to start? What do you want to start synthetically dividing by? You can start anywhere on the list. 3? Okay. I'm glad you said 3. What made you think 3? The 6. Okay. So, guys, I hope you guys remember synthetically dividing from last week. Do you? If you don't remember that from last week, you're really going to be lost here. Okay. So I'm going to put a 3 in the box. So what are my coefficients going to be then? 2, 1, negative. I think that is at a 7 and a negative 6. Cool beans. All right. So this synthetic division process, what are we going to do first? Drop the 2 like it's hot. Good. Drop it like it's hot. So we got the 7 and the 21 and the 14 and the 21 and the 15. Now, what's the title of this section? Theorems about polynomials. I don't expect you to know this one, but it's worth keeping in your brain. Do you notice how all those coefficients on the bottom row are positive? Since all those coefficients on the bottom row are positive, what we would say about the number 3 is an upper bound. An upper bound. The way we get upper bounds is we have that bottom row with all positive numbers. What that means is there's not going to be any roots, any zeros of that polynomial any larger than 3. You know what that means? It means we're going to get closer to our answer quicker. We don't have to think about positive 3 because that's not going to work. We don't have to even try positive 6. But we do have 3 roots to find, and we haven't found one yet. You want to try 2? Okay. Now, I honestly couldn't care less what process you use when you start dividing. I like to start at 1. But if you want to start at 2, you want to start at 3, it doesn't matter where you start. So I heard somebody say we're starting at where? 2 now? Okay. So we're going to put the 2 in the box. We're using the same coefficients, 2, 1, -7, -6. Here we go. We got the 2, 4, 5, 10, 3, 6. Yeah! 0. What do we think about that no remainder? 2 is one of our roots, right? And that one was in the list, wasn't it? Well, yeah, it was, yeah. So if this thing has any possible rational roots, they're going to be in the list, so 2 was one of them. So here's where some people don't quite understand what happened. What we've done is we've taken this polynomial function, and since 2 is a root, do you know what that means one of the factors is? X minus 2 is a factor, right? So x minus 2 is a factor, and that remainder that we have left, or that all that stuff on the bottom, this 2, this 5, and this 3, that quotient is the other factor, and that quotient then is 2x what? 2x squared plus 5x plus 3. You with me so far? So we're left with a quadratic. Do we need to try even in synthetic division, or can we factor this? We should be able to factor the quadratic because we're good at factoring. So let's see if we can't factor this quadratic. 2 and 3 are prime. It's got to be 2x. It's got to be x. Just got to figure out where to put the 3 and where to put the 2. 2x plus 3. And then x plus 1. Is that going to work? Okay. So what are our other 2 roots then? -1's another one. And -3/2. Now, is -3/2 in the list? It is. Is -1 in the list? It is. Keep in mind that theorem says if there are any, they're going to be in that list. Doesn't mean there's going to have to be one, but if there are, they'll be in that list. What do you think? Any questions so far? Any comments? Concerns? Short or long debates? So the question is, this is all just guess and check, basically? Yes, it's a lot of guess and check. Yeah. And sometimes you'll get to the 0 right away, and sometimes you won't. So let's try another one. Let's try example 2. Find. Now, I'm in the camp where I like to find all the roots. Some of the directions in the homework might say just find the rational ones. I want to find all the roots of y equals 3x cubed plus 7x squared. Yes, that was the evil laugh. Plus 6x minus 8. So let's think about our possible rational roots list. Possible rational roots. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. What else? Plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, plus or minus 8/3. Oh my. Now, I got to be honest with you. I like to start at 1. I don't know why, I just do. So I'm going to try 1. I put a 1 in the box. Here's my 3, 7, 6, negative 8. Bam. There's 3, 3, 10, 10, 16, 16, and 8. Now, who can say something profound? Who's been paying attention? Who's been following along? It's an upper bound. 1 is an upper bound. Well, how do we know it was an upper bound? Because this bottom row here of these coefficients are all positive. Anytime that's the case, this number that we divided by is an upper bound. So 1 is an upper bound. What that means is if there are any rational roots, none of them are going to be any bigger than 1. So that just took our list, and it took 2 out of the list, it took 4 out of the list, it took 8 out of the list, and it took 4/3 and 8/3 out of the list, didn't it? It can't be bigger than 1. It's not going to be. If there is a root, it's not going to be any bigger than positive 1. So it just basically cut our list down in half, didn't it? Now, if there's an upper bounds theorem, do you think there's such a thing as a lower bounds theorem? You're right. And what we're looking for in a lower bound is alternating from positive to negative. Alternating from positive to negative. So what should we try now? You want to try 1/3? Okay, we could try 1/3. Well, you could try 1/3. Let's try 1/3. So here's 3, 7, 6, negative 8. Now fractions freak some people out. Don't let fractions freak you out. It's no big deal. We bring down a 3. 3 times a third is simple, isn't it? 3 times a third is just 1. 7 plus 1 is 8. Now 8 times a third, that freaks people out. It's 8 times 1 over 3 times 1. So it's 8/3, right? So it's 8/3. So it's 8/3. Now 6 is really 18/3. So if I have 8/3 plus 18/3, that's going to be 26/3. Good. 26/3. Now 26/3 times a third is 26/9. That's 26/9. And 8 is really the same thing as negative 72/9. So this is negative some kind of 9ths. I don't even know how many. The fact is, or the point is, it's not a zero remainder. In our bottom row, they're not all positive, and they didn't alternate, so that 1/3 didn't really tell us anything. But it was a good try. You think maybe we should try just -1? All right. Let's try -1 and see what happens. So we put the -1 in the box. Here's our 3, 7, 6, -8. Boom. There's 3, -3, 4, -4, 2, and -2. And then that's what? -10. Hope I did that right. Does that look right? So we can't really say if this is a lower bound because these aren't, they're not alternating. Okay, if these alternated, it would have been a lower bound. So -2 doesn't work. Dang it. Or -1 doesn't work. I mean, sorry, -1 doesn't work. Yeah, we're multiplying here, right? Yeah, we multiply again on the, yeah, every time we, yeah, we're always multiplying these. Yeah, question. So a terrific question. The question is, okay, what happens if this is on our quiz and we can't find one? Well, what did we say at the very beginning of this theorem? It's possible. It's possible. It's called the possible rational roots theorem. It's not a guarantee. It doesn't say, hey, these are guaranteed, one of these is guaranteed to be a root of this. That's not what it says. It says, if the polynomial has any rational roots, it will be one from that list. But it doesn't guarantee that there's going to be one. Excellent question. So here's the deal. To answer your question thoroughly, if you divide by everything and nothing works, then you would say this has no rational roots. But we haven't divided by everything yet. So I'm hoping we can run across a lower bound. Let's try -2 and see what happens. -2, there's 3, 7, 6, -8, boom. 3, -6, 1, no help. -2, 4, -8, -16. They don't alternate. -2 doesn't help. Dang it. You want to try -4? Okay. Let's try -4. So our things we're dividing by are 3, 7, 6, and -8. Here we go. So here's 3. So that's -12, and that's -5, and that's 20, and that's 26, and that's -100 and something, right? -104, and -112. Hey, they alternate! What's that mean that they alternate? That means that -4 is a lower bound. That means that -4 is a lower bound. So none of the zeros are going to be any smaller than -4. So that means I'm not going to have to try -8 because it's not going to work. So -8's not going to work. Plus or minus 4, we already tried both of them. They didn't work. We already tried -2. We already tried -1. We already tried positive a third. So there's really not much left to try. A half is an upper bound? Well, a half's I don't even think it's in our list. Here's a shot in the dark. Let's just try 2/3. You want to try 2/3? Just for the heck of it? Just for the taste of it, Diet Coke? 2/3. We put 2/3 in the box. Here we go. There's 3, 7, 6, -8. All right. So there's a 3. 3 times 2/3. The 3's cross cancel. That's a 2. 7 plus 2 is 9. 9 times 2 is 18 over 3 is 6. That's nice. 6 and 6 is 12. 12 times 2/3, that's 24/3. That's 8. Oh my goodness. Look at what just happened. Look what you made me do. Look what you made me do. Okay, better not do that. So we got this function broken down into y equals 2x minus 3 times 3x squared plus 9x plus 12. Huh? Well, that's kind of cool. So one of our, oh, I did that wrong. I wrote that factor wrong. Who can correct me? What should this factor really be? Shouldn't be 2x minus 3. Should be 3x minus 2. Yeah, my bad. That's a neck. That should be 3x minus 2. That should be 3x minus 2. So 2/3 is one of the answers. Yeah. Yeah. So when we go to answer this, 2/3 is one of our roots. Nice. Good. So what's left then is this quadratic right here. Now it looks like we can factor a 3 out of that. So that's x squared plus 3x plus 4. And at first glimpse, you might think, well, that factors. Because 4 has factors that add up to 3, 1 and 4. But wait a minute, the signs are all positive, aren't they? Oh, gosh. So maybe it doesn't factor. So maybe we got to use that thing from Chapter 4, Section 8. Okay, Chapter 4, Section... My bad. That's in there. The quadratic formula. Remember that thing? X equals negative b plus or minus square root b squared minus 4a divided by 2a. So that's negative 3 plus or minus... Hey, wait a minute. 9 minus 16. Isn't that going to be a negative something? Dang it. That's negative 7 under the square root. Well, that wouldn't even show up on the graph, would it? Huh. Huh. So this is negative 3 plus or minus I rad 7 all over 2. Wow. So the other two roots are imaginary. What do you think? Gotta love Chapter 5. All the stuff from Chapter 4 is coming back, isn't it? Well, the title of this section is Theorems about Polynomials. And we got 2 more, and they're very similar. And I know that's not a word, but I like to say it anyway. The other 2 theorems are very similar. They're called the CCT, and they're called the ICT, not to be confused with ICP. Anyway, CCT is short for the complex conjugate theorem, and here's the short and sweet version of it. It says if a plus bi, if a plus bi is a root of a polynomial, then so is a minus bi. Now, in case you're wondering what those abbreviations stand for, C stands for complex, C stands for conjugate, and of course T stands for theorem. So that's the complex conjugate theorem. It says complex roots show up in pairs. It says complex roots show up in pairs. Pairs being spelled P-A-I-R-S, not inside of the fuzzy things. Or those are peaches. I always get peaches and pears confused. Pears are the yellow things, right? That are kind of like an apple. Okay. Yeah, so if you core a pear, you're not going to find a complex root in there. You might find some seeds. All right. So the other one, the ICT, stands for irrational conjugate theorem, and it says this. It says if a plus rad b, if a plus rad b is a root of p of x, then so is a minus rad b. So this is saying that irrational roots show up in pairs. And we just saw this from the quadratic formula. We could imagine that for either case because of the plus or minus bit from the quadratic formula. These things always show up in pairs. So we've got 2 more examples to look at, one of which is really easy, and the other of which gave our former administrator, who was a math teacher for 9 years, trouble. Yep. So here we go. Example, what are we on? 3. Example 3. 3 minus 2i and 5 halves are roots of f of x. Are there any others? Are there any others? Question mark. If so, what are they? Question mark. So 3 minus 2i and 5 halves are roots of f of x. Are there any other roots of f of x? Yeah, what are we thinking? Okay, we're thinking yes, there are. What are we thinking the other one is, or the other ones are? 3 plus 2i, because of, what kind of numbers are 3 minus 2i and 3 plus 2i there? Are those irrational or complex? Complex. So by the CCT, this is 2. By the complex conjugate theorem, 3 plus 2i is also. Are there any others? Do you think negative 5 halves is one too? Well, hold on a minute. What were the theorems? The theorems were the complex conjugate theorem. 3 minus 2 halves is complex, and the other one was an irrational conjugate theorem. Is 5 halves irrational? 5 halves is irrational? It can't be written as a fraction? 5 halves is rational. There's no such thing as the rational conjugate theorem. So that's it, just the 3 plus 2i. You picking up what I'm putting down? Okay. Last example, here it is. Example 4. A polynomial g of x has negative 4i and 3 plus rad 2 as roots. Write it in factored form. We'll worry about multiplying these tomorrow, okay? Because we're not going to take the time out to try to multiply these out today. But some polynomial has negative 4i and 3 plus rad 2 as its roots. Write this polynomial in factored form. Now, what's the degree of this thing going to have to be? Did you say 4? How'd you know? Both of them fall under the theorem. So because this negative 4i is a root, what is also? 4i is also. And because 3 plus 2i is, what else is 2? 3 minus rad 2 is also, right? So in factored form then, we're going to have g of x equals x minus negative 4i. Wait a minute, minus 4i. That's plus 4i. So I have x plus 4i. So this particular factor comes from this particular 0, to be clear. And then we said 4i is also 1, so we'll have x minus 4i. So this particular factor here comes from the fact that 4i is a root. X minus the quantity 3 plus rad 2. So in case you missed it, this comes from the fact that this 3 plus rad 2 is a root. And then there's one more factor, right? What's the last one? X minus the quantity 3 minus rad 2. Yeah. Now, multiplying that out takes about 15-20 minutes, so we'll do that on tomorrow. Okay. So that's it for today. It's been real. It's been fun. For exercises, you'll be listing possible rational roots. You'll be trying to find some roots. And I think you'll be writing out polynomials. And if it says write them out in standard form, I just want you to write them out in factored form. I'm good with that. Any questions? I'd like to give a shout out to the future Mr. Minnick for being so awesome. Have a great day. Good.